Welcome, everyone, and nice to see you here to our next episode of Maritime Innovation Updates. We have our last episode in January, but we'll continue, of course, with the next ones in February. The presentation today is going to be about Lidar-based obstacle detection. But before we get started, I would like to kindly ask you to keep your microphone shut off, as well as your cameras. You will have a chance at the end of the presentation to ask questions, or if you prefer to do it, you can also leave them in the comment section. They will be answered by our speaker today at the end of the presentation. That being said, I will introduce the subject. So today's presentation is going to be delivered by my colleague Nico Tantop. Nico Tantop is a research associate at Fraunhofer Institute, and his research focuses on unmanned vehicles, perception, and general control and navigation for surface vehicles. Today's subject is about lidar-based obstacle detection and path prediction for unmanned surface vehicles, and it focuses on ways of detecting and participants in the maritime traffic in order for enabling autonomy for unmanned surface vehicles. That being said, Nico, you have the floor.
Thank you, Cosman. So, hello everyone, also from my side. Yes, today I want to talk about LiDAR-based obstacle detection. And first of all, I want to start with a brief introduction or background where we worked on this topic. So we basically have a project that is called Digitales Testfeld Elbe, where we work together with Fraunhofer IFF and Torsis and also Galileo Testfeld in Magdeburg. And our goal is to build a digital foundation or data foundation of the Elbe River and how we can utilize unmanned surface vehicle, for example, for bathymetry surveys. And in this part, as Fraunhofer CML, we worked on an unmanned surface vehicle and we worked on the part of obstacle detection, especially when we are in an area where we have other moving objects. And this is now a situation that can occur, especially when we perform like a bathymetry survey or collecting other data sets. And the problem is if we use classical approaches where we don't have a path prediction also of the vehicle, or if we use clustering approaches using LiDAR sensors, especially in these small areas, we can have problems with the clustering, and clusterings get really big. So we developed an approach that can detect especially moving objects with a LiDAR sensor. And we developed like a big pipeline that we can use to predict the moving objects and also predict the path of the moving objects. The pipeline consists of 3 different stages. So we have like data sources that are the LiDAR sensors and also the navigation devices that get the information about the localization, the position and the heading and the orientation of the ship. And then we have the point cloud pre-processing. The problem when using LiDAR sensors, the information or the data stream is really, really big because it produces a lot of data points. So we have the first stage that is the point cloud pre-processing with the goal to clean up the point cloud and to make the data reduced in size. And the second task is the environment mapping and the object detection, where we actually detect the object in the environment. And the third part is the object tracking. I want to go into the details of each task later. For this project, we used our vehicle CML Sea-Line. It's one of our unmanned surface vehicles that we built ourselves. It's autonomous electrically driven vehicle that we can use for our research in autonomous systems. Coming to the first stage, the point cloud preprocessor. The goal of the point cloud preprocessor is to clean up the point cloud and to reduce the size. It consists of multiple stages. So the first one is downsampling of the point cloud using voxelization technologies, and this reduces the point cloud size for lower computational load in the later process. Then we have a pass-through filter that removes like the USV as itself, because it also produces some noises. For example, the waves can also be reflected, and then you also get measurements of the waves. So you need to remove also the noise of the vehicle, and then later on also the noise of the surface. In the next step, we use the navigation device like the sensors that predicts like the position and the orientation to make a coordinate transformation to stabilize the point cloud. This is needed to remove the water surface. This is now the fourth step in the point cloud preprocessor. Now I have an example where you can see this is now a point cloud, how it looks like when it's recorded raw, and you see in the white spot there's the USV that is currently moving, and it produces like waves, and you have like this disturbances. And now in yellow you see the boat we want to track, and this one is also moving, and now you see the point cloud stabilized and also the noise is removed. Like in white now you see the noise of the vehicle that we use to detect other vehicles is now removed, and also the point cloud is stabilized. Coming to the next step, it's the environment mapping and object detection. The goal here is to detect like all the objects in the environment that are moving, and detect like the center points to use it in the later stage. What we here do, we use the cleaned up point cloud and using the ICP algorithm to attach it to the big point cloud and make a big map out of it. And then we have two stages where we create like an occupancy grid, like it's basically like a two-dimensional grid where we can give each cell a value, and each cell is like a prediction if the cell is a static obstacle, a dynamic obstacle, or if it's unknown. And on this occupancy grid, we perform a clustering, and then we compare the old and the new clusters to make prediction of each cell to get like an estimation if it's a static obstacle or a dynamic obstacle. And when we compare the new and the old point clouds that we already recorded, we can estimate like the moving parts, and we can estimate like the center points of these moving parts. And then we get a prediction of the center points. This is like the pipeline that we use to predict the center points. To showcase, I also have like one example here where you can see this is now a mapping when we recorded it 15 seconds, and in green you see now the vehicle we want to detect. And now 15 seconds later, you see movement of the USV and also of the vehicle that we want to detect. And coming to the example here, now you can see how a occupancy grid could look like, and you see like a path of the vehicle. Now these object centers, or the predictions that we get of the vehicles in the surroundings, we feed into like an object tracking algorithm. For that we use like a simplified model. It's a constant turn rate velocity model that we use for unscented Kalman filter to predict like the states of the vehicle. So basically what we do, we have a continuous update of the sensor readings from the Lidar or of the object center points, and we check if these center points were there before and if they are in range. And then we also have some kind of tracking. And we create dynamically like new UKF instances if there are new objects or if objects leaving the area that we are observing. And what we get out of it, we get like a position and a heading estimate of the vehicles. And now I want to showcase our results that we get with this pipeline. We tested all of this in our harbor environment in Hamburg. In front of our building, there's like an area which is like approximately 200 meters long, 65 meters wide, and we use as a target boat one of our manually driven boats as a target boat and the vehicle I showed in the beginning. We recorded different scenarios, or we created 5 different scenarios to validate the performance of the pipeline. You can see all the 5 scenarios here. It's like scenarios that can occur when you are moving in a harbor environment. For example, crossing of 2 vehicles going the same direction, overtaking maneuver, and some zigzag maneuver as well. On this slide, now I showcase the results that we get with each of the maneuvers when we validated the performance of the pipeline. In average, we got like a root mean square error of around 3.8 meters when predicting the center point of the black ship that you can see in the scenario images. Here's now an example how a prediction can look like. In blue, you see the path of the unmanned surface vehicle. In red, you see the ground truth of the black ship. So we basically attached a second sensor or GPS on top of the black ship that gave us like a ground truth position of the object detection. So we can validate our performance of the developed pipeline. And in green, you see the prediction of our pipeline of the vehicle's position in XY position. Now here's a second use case. And now I want to showcase also the path prediction. So you see now 3 crosses, and the crosses are like the points where we assume we don't get any new reading of the Lidar sensor. So the predictions rely on the old sensor readings, and what we see here, we have this constant turn model that the prediction also relies on this constant turn model, and it predicts like with a constant turn the path of the detected ship. But what we also see in red and green, so basically in green you see if there are new sensor readings, we get a better prediction, but if we don't get any new sensor readings, we assume like this path and we can predict this path. And especially in this case, when we work on the path planning part, this one would be a good prediction, because then we are on the safe side, because we would stop or create a new path that is around of this vehicle. Now I go to the conclusion. So basically we developed like a perception pipeline to detect like dynamic obstacles and predicted a path of dynamic obstacles in harbor environments, and we overcame the limitations of traditional methods in narrow, crowded environments. The innovation approach here was to use the occupancy grid for static land removal, and we improved the obstacle avoidance by integrating dynamic obstacle trajectories. Further enhancements, we are currently also working in an AI-based approach. We collected a lot of data with our Lidar sensor, and we labeled them with for using it for AI-based approach, and we are currently training a CNN point pillar approach to predict the objects based on AI, and maybe we see the results of it in our next maritime innovation update. Yes, so that's it from my side, and if you have any questions, feel free to ask them now.
Thank you very much, Nico. This was a very interesting presentation. Maybe just to start off the questions, I would like to ask you whether this information that you presented today is somehow available in some publication so that people could, or we could look into the results a bit more in depth.
Yes, so basically this is something that we worked on and published last year on the ICMAS conference, and you can find this paper with more details on this topic also online.
Mm-hmm, mm-hmm.
And it should have the same name of the presentation.
Perfect. So we'll Google Scholar you then. In the meantime, are there any questions in the chat window, or is anyone willing to pose a question directly on the microphone? Okay, maybe some people are writing there or thinking of their questions. I will maybe pose my personal question, what would happen if, harbors are very cluttered environments, and maybe when you cluster the ships that are docked, some of them would be seen, just half of them from their actual shape, or a part of them will be seen or enclustered by the Lidar. What would happen in this case? Where will you put the center point of the vessel? What will happen with the detection? Will this have any impact?
Yes. So basically, I have one slide as a backup for this one. So basically, you can now see we can have a false detection or a wrong detection of the center or the bounding box. And basically, what we're currently working on, especially in the project like Digitales Testfeld Elbe, we want to also work on the technology vehicle to X, where two different vehicles can interact. And we are already working on solutions, or we are looking in developments where two USVs can work together and you can merge the resulting bounding boxes. And also we are working on a solution where we use additional information. For example, from an IES sensor, maybe we can get the information about the ship, or the third approach is to have some kind of memory, because you have multiple readings or multiple predictions of the vehicle, and maybe you saw the vehicle with one USV from different angles, and then you can store this information in the algorithm, and you get a better prediction over time. So maybe the prediction is not that good at the beginning, and you can improve it over time when you have multiple readings.
Clear. Okay. Thank you very much. Are there any other questions from the public? Well, it means that the presentation was very, very clear to everyone. So thank you, Nico, for presenting us this very interesting topic, and for the research itself. I think it's very promising, and we'll be looking into new perception modules or output of perception modules for unmanned surface vehicles in the future, thanks to this possibility of understanding the vessel traffic through Lidar. So what do we have for next week planned? Next week, we're going to have another episode of our MIU. This time, we'll be going in the direction of water-based or like hydrogen-based estimation for imports. It's going to be a slightly different topic, more into the logistics, and my colleague Patrick Zimmerman will be hosting speaking for the subject. Therefore, please register for this MIU, and we are looking forward to seeing you and hearing you in the next episode next week. Until then, have a great weekend.
Thank you. Bye bye.